Alright, today I'm going to show you the differences between series and parallel circuits. I'm also going to show you how to solve for the current and voltage through each component in both of these circuits. See, each of these circuits is made of a battery and two bulbs. But there's a critical difference between these two circuits, and that is how the bulbs are wired to the battery. And to understand why the wiring is so important, we need to take a look at a charge coming out of each battery. In a series circuit, a charge comes out of the battery along this wire and travels first through one resistor, then through the other resistor, and finally back to the battery. There's only one path along which this charge can flow. Now, on the other hand, in a parallel circuit, a charge comes out of the battery and travels along this wire, but then the wire splits. Now, the charge can't go down both this wire and this wire. It has to go one way or the other. So unlike a series circuit where there's only one pathway for the charge to flow along, a parallel circuit has multiple pathways. And that causes this parallel circuit to behave in a completely different manner than our series circuit. So to really wrap our head around what's going on with each of these circuits, we're going to do something called analyzing each of these circuits. And really all that means is we're going to solve for the current and voltage across each of these bulbs in each of these circuits. So starting with our series circuit, the first thing we need to do when analyzing any circuit is solve for what's called the equivalent resistance of the circuit. Now, equivalent resistance is, simply put, the total resistance of the circuit, or you could even say it's the resistance which the battery behaves as though it's connected to. Now, equivalent resistance in a series circuit is given by the equation equivalent resistance is equal to the sum of the individual resistances of the resistors, or in this case bulbs, in the circuit. Now you'll see there's only two bulbs in this circuit, R1 and R2, but you can continue adding as many resistors as you want in series according to this equation. So really the equivalent resistance in a series circuit is nothing other than the sum of all of the resistances, which in this case is 15 ohms. Now the reason the equivalent resistance is so important is because it allows us to solve for the current which is coming out of the battery. See, by applying Ohm's law to the battery using the equivalent resistance, we can solve for the total current. So knowing our battery has a voltage of 1.5 volts, and the equivalent resistance is 15 ohms, we find the total current coming out of the battery is 0.1 amps. Remember, we're trying to solve for the current through each resistor as well as the voltage across each individual resistor. Now, because this is a series circuit, these 0.1 amps of current which flow out of the battery have to also flow through each resistor. That means there's going to be 0.1 amps of current through this bulb, and 0.1 amps of current through this bulb. It's a common misconception to think that the current somehow gets used up or disappears as it passes through a resistor. The current, remember, is just a bunch of charges or electrons which are flowing through these wires. The electrons can't disappear or get used up. They have to keep flowing from one side of the battery all the way through the circuit to the other side of the battery. Now remember, we're not only trying to solve for the current through each resistor, we're also trying to solve for the voltage across each resistor. And knowing the current and resistance at each bulb, we can solve for the voltage which is used up at each bulb. So using Ohm's law, looking at bulb 1, the voltage across bulb 1, or the voltage drop across bulb 1, is going to be the current through bulb number 1 multiplied by its resistance. And we find the voltage drop across this resistor is 0.5 volts. That is to say, it's using up a half of a volt of electric potential. Doing the same thing for the second bulb, we find the potential drop, or the electric potential used up in this bulb, is 1 volt. There's a big conclusion we can draw about voltage from these two results. I want to point out, it's not a coincidence that the voltage across the battery, which is 1.5 volts, is equal to the total voltage which was used up in going through the two bulbs. If you think about the potential which a charge has as it leaves the battery, when it first leaves the battery it has 1.5 volts of potential. And as it moves along a wire, it doesn't lose any potential. We say our wires are perfect, or they have no resistance. So when that charge gets right here, about to enter this bulb, it still has 1.5 volts of potential. Now as it passes through this bulb, we know it's going to lose 0.5 volts of electric potential. So 1.5 volts minus the 0.5 volts which it's going to lose will leave it with 1 volt of potential as that charge exits this resistor and enters this wire. Then it travels along this wire and enters this bulb with 1 volt of potential. And we know as it passes through this bulb, it's going to lose 1 volt of potential, leaving it with 0 volts. And so that charge will continue back to the battery. And we find that the total voltage of the battery has to always equal the total voltage used up by a charge in the circuit. Now moving on to our parallel circuit. The circuit is wired up differently than our series circuit. Now moving on to our parallel circuit. The circuit is wired up differently than our series circuit, so things are not going to go the same way as before. The circuit still obeys Ohm's law, and we're still going to follow the same steps to find the current and voltage through each resistor, but the equivalent resistance in a parallel circuit is found using a different equation. So the equivalent resistance for a parallel circuit is given by one over the equivalent resistance equals 1 over R1 plus 1 over R2, and so on and so forth. So to solve for the equivalent resistance of this circuit, we're simply going to plug these numbers into this equation for the equivalent resistance in a parallel circuit. And we find the equivalent resistance in this circuit is 3.3 ohms. See, the big difference between a series and a parallel circuit is that as you add resistors in series, you continue to increase the equivalent resistance. But in a parallel circuit, as you continue to add more and more resistors, you effectively decrease the equivalent resistance. Because every time you add a resistor in parallel, what you're really doing is you're giving the charges another pathway along which to flow. But just like when dealing with a series circuit, if we want to solve for the current and voltage across each of these resistors, we need to first solve for the current coming out of the battery. So using the same equation as before, and plugging in our values for the voltage of the battery and the equivalent resistance, we find the total current coming out of the battery is 0.45 amps. And just like before, we're going to solve for the current and the voltage across each of these bulbs, but we have to be a little bit clever in solving a parallel circuit. See, when we're dealing with a series circuit, we knew the 0.1 amps that came out of the battery was going to travel entirely through this bulb and then entirely through this bulb. So we knew the current through each bulb. In this case, because the current splits, we can't do that. So what we instead need to do is, rather than looking at current to solve this problem, we need to look at potential, just like we did over here. And just like with this series circuit, when a charge comes out of this battery, it has 1.5 volts of potential. And as it moves along a wire, it's not going to lose any potential. So when a charge gets right here, it's still going to have 1.5 volts of potential. Now, whether that charge goes along this wire or this wire, it's not going to lose any potential. So a charge that travels down this wire to this bulb is still going to have 1.5 volts of potential when it reaches this bulb. And it'll still have 1.5 volts of potential if it travels down this wire to this bulb. Now we also know, just like over here, that the charges entering the battery have to have 0 volts of potential left. So a charge entering right here is going to have 0 volts. Well, if we backtrack along these wires, we know a charge coming out of this resistor is going to have 0 volts of potential. And the same goes for this resistor over here. And so if you look at what we've done, we've found that there's 1.5 volts of potential across this bulb, or you could say 1.5 volts are used up as charge travels through this bulb. And the same goes for this bulb. So applying Ohm's law to this bulb first, knowing the voltage used up across this bulb is 1.5 volts, we find the current through this bulb is 0.3 amps. And doing the same thing for this bulb, knowing there's 1.5 volts of potential across this bulb, and it has a total resistance of 10 ohms, we find the total current through this bulb is 0.15 amps. So much like in a series circuit where the voltage of the battery was the same as the voltage used up in the circuit, we see in a parallel circuit the total current coming out of the battery is equivalent to the total current which passes through all of the resistors combined. So we've seen that whether you're analyzing series and parallel circuits, you always solve first for the equivalent resistance, then the current coming out of the battery, and from there you're then able to solve for the current and voltage through each individual component within the circuit. Now, one last thing I want to point out while we're talking about series and parallel circuits is that in a series circuit, if this bulb was to say burn out, it would prevent current from flowing through this bulb, which means no current would flow anywhere in the circuit. That means this bulb would in turn go out. This is like an old strand of Christmas lights. One bulb burns out and they all go dark. In a parallel circuit, if this bulb was to burn out, there's still a pathway for the charge to flow along, which means this bulb right here would still have charge flowing through it and it would stay lit. And on that note, that's all for now.